Good morning, everybody. Looks like we've already got a good crowd here. So welcome to the code walkthrough for Dmclock, the implementation of a algorithm for distributed quality of service. Eric, if you want to take it away.
Sure. So this was an effort by me a few years ago to try and improve the fairness within Ceph and the OSDs. And so it was the focus of my work for quite a while, but actually I probably haven't touched the code in a couple of years at this point. So this morning I've been kind of going through reviewing it and trying to remember how things were organized, why I did certain things certain ways. And then more recently, other people have kind of taken on Dmclock. So within RGW, I think both Casey Bodley and Abhishek, who's also, I think, on this call, have done quite a bit of work with Dmclocks in the RGW space. And Sam Just has done reworked quite a bit of it on the core side as well. So anyway, so they, especially Sam, might have a stronger knowledge at this point of how things are organized. But I'm happy to go through and share things. And anyway, let's go from there. So I'd first like to I created a few images just to kind of help organize people's thoughts on how this has worked, or how this works. And so now let me see if I can share my screen, or at least start sharing some windows here. Share first. All right. Are people seeing my shared screen?
Yeah, we can see the Dmclock paper.
Right. So this is the basis of everything. This is kind of the one paper that describes the algorithm, the mclock algorithm, and then also the Dmclock algorithm in quite a bit of detail. So everything kind of comes back to here. Now, over time, we did kind of find areas where things weren't working as we would expect it. So we've made a few deviations from the algorithm as described here. But for the most part, it follows it pretty religiously. The second thing to realize is that Dmclock was written as a library that could be incorporated in a variety of contexts. So the library itself is simply some header files which are heavily templatized, and some other code which actually does get compiled. But because of the templates, you can use them in a variety of circumstances. It's not written for Ceph specifically. So, in fact, it has its own GitHub repository. It's a submodule of Ceph, and other people could actually use it for entirely different projects altogether. So, the paper is available online, and for those of you looking at the code, it might help explain certain things if certain questions do arise. Let me switch to a different window now. All right. Now, the paper describes the mclock algorithm and then a variation of it called the Dmclock algorithm, which stands for distributed mclock. And the idea is that you have multiple servers that can handle various requests and multiple clients as well. So this is kind of looking at distributed mclock. And for any given request, a client might direct it at any one of a number of servers. Now, this fits very nicely in the Ceph world because the servers are basically OSDs, and you can imagine clients, figuring out which OSD gets a given request and sending it to the appropriate OSD. But we want to ensure fairness among all clients, no matter which server or servers they're sending requests to. And so one of the nice features of the Dmclock algorithm is that the servers are not sharing information among themselves about the clients. The servers are simply getting requests, servicing the requests, and the responses back to the clients. It's the job of the clients to keep track of which servers have successfully handled requests for them and keep track of those internally. And that way, every request to a new server can give like a little bit of knowledge, a little bit of history of what kind of service that client has received from other servers, and that allows the server getting this request to weight things appropriately. So if this client has been getting a lot of requests serviced by server 1, and the next request goes to server 2, server 2 will say, okay, your needs are being met or have been met in the recent history because of server 1, and therefore your request might not be rated as highly as some of the other clients. And so this distributed aspect happens strictly on the client side, and simply they're reporting back with every request kind of the level of service they've achieved recently. That's kind of an interesting thing about how Dmclock is organized. The other thing is that the term client can be used relatively loosely. So the typical environment is that we actually have different clients, people wanting to use Ceph for various purposes, and each of them gets to send some requests to the server. But when this was originally used within Ceph, clients was used far more broadly in that we wanted to be able to adjust how servers were handling requests from actual clients, but also handling background processes. And I don't remember what the names of the background processes, but different kinds of cleanup processes and whatnot that have to occur in order for a Ceph cluster to run smoothly. And so we had one client was specifically for clients themselves, and then we had different other clients used for different background processes. So we could give those lower weight or reserve fewer slots for them. We want those background processes to run and accomplish their goals. We want to balance those against requests from actual clients. And so there literally was just one of these clients was literally for clients, all the other clients, all the Ceph clients, and then other clients were for specific background processes. Now, this is one area of code that's changed quite a bit since I last touched it. I was just looking at the code, realized I didn't recognize it, and Sam just has completely rewritten all of this code here. We'll take a quick glance at it during the code walkthrough, but he's adjusted things quite a bit from where I had last left things. Okay. I don't know if people can ask questions whenever it's most convenient for them. Maybe I'll just ask, are there any questions at this point? Okay. Let me see if I can help organize things here a little further. So the server has this idea of clients. Each client has a queue of requests that have arrived for the client. Again, we're using the term client very loosely, but probably you just want to understand the algorithm itself. It probably makes sense just to think of clients as true clients here. And so you'll see that we have n different clients here. Each client has a queue of requests. The first request in each queue is here on the left and is highlighted in red. Okay? Now, each request has a tag that goes with it, and the tag includes its reservation, its limit, and its weight. All right, we actually assign these actually by clients as opposed to every single request. We don't have to keep repeating information again each time, and that helps determine which request is handled next by a given server. So one server has all these clients, has these requests lined up, and it's looking only at the first request for each client in order to determine which request to service next. So for any given client, the requests are handled sequentially. All right. The only question is which client gets its request handled next, and so it's looking at the first item in each of those requests. So at this point, I don't know if this is as organized as I could make it. Let me actually start looking at some code here. So let me share a different window. So as you can see, the Dmclock source code submodule within Ceph Here's the top of the Ceph tree. Then we go to source, and then we have Dmclock, and then we have its own source directory from there. All right. And if we look in this directory, actually, let me pop up one level first. At the Dmclock level, we have some files for making things and whatnot. We also have a source directory which has the source code for Dmclock itself. We have support, which specifically has one data structure, which is key to how the server side is implemented. It's called an indirect intrusive heap. So we'll take a look at that. It, of course, has some testing code. And then when I was developing it, I wanted to make sure it was running as I was expecting. So there's actually a little bit of a simulator in here as well to actually simulate a bunch of servers and clients and using the algorithm itself to see how the requests are serviced and so forth. So that was useful during the development and could also be useful for those trying to understand how everything works. But let's first take a look at the source directory here. And you'll see that there is a header file for the client side, a header file for the server side. Then there is a header file for some records, some structures. And it's actually relatively small, but these are structures that are shared between both the client and the server side, so they only have to be defined once. There's also some utility code as well that can be used by either the client or the server. And just to get a quick look at the Rex file, it's actually not that big. That's the entire size of the file here, and basically defines a counter type, a phase type, whether a given request is handled during the reservation phase or the priority phase. And the request params, these are params that come in with each request that contain these values called rho and delta. Again, these are the values that each client sends in with each request, which describe the level of service that client has received from other servers. And that allows a given server with a given request to appropriately prioritize this request. So if it's been getting a lot of service from other servers, it's not going to get the request is going to be lowered in the priority as compared to other requests from other clients. Okay, so that's really all that contains. And actually, the numbers or the values that are contained within these are delta and rho. Delta is how many replies the client has received since its most recent request. Okay, so it's just simply saying, I've received 5 replies since my most recent request, because requests go out and then there's a delay before the replies come back in. And then rho is how many of those requests were handled during the reservation phase. Again, there are 2 phases that Dmclock runs at. Reservation means kind of the minimal level of quality of service that we're trying to give to a given client. And so we first try and achieve the minimum, the reservation for every client. Once every client has achieved its reservation, we then switch to a priority phase where we use a weight value to determine which request is serviced next, right? And so rho simply counts of those recent requests, how many were handled during the reservation phase. And then simply by subtraction, you can determine how many were handled by the priority phase. So it's simply 2 extra integers that are sent in with each request that determine, that describe the level of service a given client has received from other servers. Okay? Now, the client code is a lot simpler, so why don't we start there? Okay? And again, I would like to invite people to ask questions along the way. And in order to, for people who want to use Dmclock, keeping track of rho and delta is a little bit of a chore itself. So there's actually a data structure designed to do that, and that's called a tracker. And two trackers are provided for in this source file. One is called orig tracker, which is the original tracker as described in the Dmclock paper, implemented as closely to that as we could figure out at the time. All right. And then there was an alternative that was developed as well called the borrowing tracker. Okay. And I'm not actually sure. I'll have to look at the code to see. I don't know if, as the original tracker evolved, there were lots of discussions between many people in the open source community, especially a lot of colleagues or contributors, I should say, in Asia, who were really interested in Dmclock and really providing a bunch of feedback, doing analyses on how it was operating and so forth. And there was long discussions about how the original tracker was intended to work. And I believe now the borrowing tracker is no longer used because some tweaks were made to the original tracker, probably maybe as the original paper originally wanted them to be handled, but there was some ambiguity in interpreting the paper. But I think the original tracker is the only one that's being used at this particular point in time. And as you can see, it has a function here called prepare request that returns the request parameters with a delta and a row, and then calculates the next delta and rows as well. And then when a response comes in, I remember exactly how this works here. The phase at which that the request was handled, whether it was the reservation phase or the priority phase, is returned back, and then deltas and rows are updated as a result of that as well. Okay. Coming down below here, we have this thing called the service tracker, which then takes one of those two trackers. That's the template T, and by default it uses the original tracker. And then we need some way to identify each of the different servers. And we don't want to bake this in because we want Dmclock to be as flexible a library as possible. So however we track servers, it could be strings, it could be integers, it could be what, that is passed in as the first parameter to the template. All right? It keeps track of a variety of things here, including all the various servers and the different requests going out to them. And then basically, as I can find it here, when we have a request ready, we call this get request params function, passing which server we're going to send the request to. It determines what the additional request params are that need to be sent along with the request that include things like delta and row and so forth, and returns them back out. So those can be sent back in. And then when the reply comes back in, the client will call this function track response. Specifies the server ID, which phase that happened in, and what the cost of the request was. And it then uses that to then update the information about that particular server and so forth, so the deltas and rows can be tracked appropriately. So for the client, there's just a little extra effort involved in calling one function when a request is ready to be sent to the server, and then another function to call when the response comes back from the server. Now, at some point, we introduced this idea of cost into this, and that is because not all requests have the same cost. So some read requests might ask for 1K, some might ask for 16K, and those might have represent different costs to the server. Write requests might be more costly to the server than read requests. And then there may be requests that are actually composed of multiple sub-operations and so forth, and those requests might be more expensive than other requests. And so we have this idea of a request, which is basically an integer, which is basically kind of a factor saying that this request has a cost of 5. So consider it to be like, if we have a minimal request, consider it to be equivalent to 5 minimal requests. And therefore, when a reply comes back and the server says this was really a 5, not a 1, we send that back into this track response function so that the deltas and rows can be updated appropriately saying that we essentially got 5 requests handled with this one request because it was such an expensive request. All right? So it gets a little bit complicated here, but for the client, you just simply create a service tracker, and then you call these 2 functions with each request and each reply, respectively, to track things on the client side. So are there any questions about that before I move on to the server side? All right, this is definitely the more complicated aspect of the algorithm here. And it's all in a header file because templates are being used to create as much flexibility as possible for those who want to use this library. Yes, I'll just kind of come down and look for the interesting things here. So for every client, we have to keep track of certain information about the client. What its reservation is, again, that represents the minimum amount of service we're trying to give to that client. The weight, and the weight is used once the minimum service is achieved. We then use the weight to determine which client gets its request next handled. And then there's also a limit. We can put a cap on the level of service we give a specific client as well. And so that, again, only comes during the weight phase, the proportional phase of this, and that only clients who have not reached their limit are considered when we choose the next request via the weight or the proportion. Unfortunately, I think the code uses both weight and proportion, and they're essentially equivalent. But unfortunately, different parts of the code use different terms. That's something that could be corrected here. All right. We also keep track of the inversion of all of those. So 1 over the reservation is the reservation inverse. 1 over the weight is the weight inverse, and so forth. We also allow a 0 to be given for the reservation, the weight, or the limit, which means that we don't care. All right, so if we give a 0 in for the reservation, that means there is no reservation, there is no minimum level of service, and only when the reservations for all of our clients have been met will we then have our weight will be used to determine if we get some service as well. Weight, if the weight is 0, that means that we're only going to handle things based on the reservation, and if the limit is 0, that means there's no limit for this particular client, there's no cap on it. So each of those could be 0, and because they can be 0, when we calculate the inverse, we have to be a little bit careful there. Right? We then come down to a request tag. All right. So, so the request tag, as you can see, contains the reservation, proportion, and the limit. Okay. Also the delta and row that came in with the request, the cost as it was calculated, and whether this request is ready. And as I recall, ready means that that we have not hit the limit. If we hit the limit, then this is not ready. Okay. And again, this is used during the wait phase of Dmclock. Okay. So there's a code here to calculate the request tags. All right. And then we start getting to the meat of the algorithm here with this templatized class called priority queue base. All right. And there are a number of template parameters that we can use to tune this for various purposes, okay? So C is the identifier for clients. Again, we don't want to specify that a priori, so this could be a string, it could be an integer, it could be or it could be a structure that identifies the various clients we're using. R determines what the structure is that the requests are comprised of, that we have to keep track of in our queue somehow. Is delayed was an optimization, I believe, added by Casey Bodley, which is that when do we calculate the tag for a given request? Now, originally, every tag was, actually, I'm not sure it was Casey. It might have been one of the contributors in Asia who contributed this. But basically, originally, the tag was calculated when the request came in and would use the most recent row and delta for that client that it knew of at that time. This optimization where we delay the tag calculation actually makes Dmclock work better, in that we calculate the tag once a request achieves be the head of the queue for that particular client. And that allows us to use the most recent row and the most recent delta to calculate the tag, allowing it to use the most recent information, which allows the algorithm to be as fair as possible. And then we have the B parameter. There's a heap that's being used actually multiple heaps. There's 3 heaps being used to track all the different clients. And with the heap data structure, you can use a fan-out factor. By default, it's typically 2. We had one student, a graduate student, who spent a summer looking to see whether we could optimize the fan-out for the heap. And I believe that he ultimately determined that 3 might have been slightly better than 2, but it was 2 or 3. You can specify that here. I forget whether this is a base class, and I believe the subclasses have the default for that. It's either 2 or 3. And finally, there's this other Boolean parameter, which determines whether the client information, that is the reservation for the client, the limit for the client, and the weight for the client, are determined dynamically. So if the clients can possibly change those values, a client can request maybe a higher level of reservation, that there's a higher minimum level of service, that can be changing all the time. And so either once a client is introduced to the queue, we simply leave those values static for that client, or do we occasionally re-query the client and say, what is your current reservation? What is your current limit? What is your current weight? And update our internal data structures based on that. Of course, if we have to keep on querying the client, that requires a lot more. That requires some additional work and slows things down a bit. So we only want to do that if necessary. So it really depends on whether this is being used in a more of a static or dynamic situation where clients could possibly alter those values. And that's why this is a Boolean here. Okay? There's a lot of bookkeeping involved in Dmclock, so I won't go through all of that in great detail. But here's kind of the next interesting piece of it, I think. And that is we have this data structure called an indirect intrusive heap. And we can pop into that. That's going to be in that support subdirectory of the Dmclock subdirectory. But we actually have to keep track of 3 different heaps. One for the reservations. We want the heap data structure, for those of you who aren't familiar with it, is often used in priority queues for a couple reasons. One is that it keeps its data in contiguous memory, generally speaking. And so it can really take advantage of CPU caches as it moves things around within the heap. Because it's all contiguous, it can often be done in CPU caches. It has a log n. Most operations have a log n, order of log n. What's the word I'm looking for? An order of log n. All operations are order of log n, which means they're relatively inexpensive. And really, it doesn't have to keep all the elements within it sorted from first to last. It's simply, for a priority queue, you simply need to know which has the highest priority at any given moment. And so it simplifies things by only having to track what the most highest priority item is within the heap. So it's a very good data structure to use. And in a second, we'll come back and take a look at this in a little bit more detail. But we need to know which client has the next thing with respect to reservation. All right. We also need to know which clients are still within their limit. That if a client has gotten a lot of their request serviced, they may be outside their limit and they may not get any attention for until we get back below their limit. And then once we've satisfied all the reservations, we need to go by weight. And the ready heap is a heap that contains only those clients who have not exceeded their limit, and then it orders things by weight as opposed to by the reservation. So reservation heap orders things by reservation, limit by limit, and the ready heap has two factors in things. One, things that are at their limit are at the end of the heap, and things that are still within their limit are at the front of the heap, and then within that, we use the weight to determine how things are ordered. All right? And again, I'm going to switch windows here, give you a picture. All right, so hopefully you're back at the picture of the server view. And the elements in the heap are each client. So client 1 is one element in each of these heaps. Client 2 is one element. Client 3 is an element. But they're ordered based on the tags for the first request in each of those queues. And so the request that has the lowest reservation will be at the top of the reservation heap. The request that has the lowest limit will be at the top of the limit heap. And then the request that has the lowest, really kind of the great, who's next in terms of weight will appear at the top of the ready heap. And so since each of these clients has to appear in 3 different heaps, the heap doesn't contain the client itself, because the same client can't appear in 3 heaps. There's simply a record in each of those 3 heaps which refers back to each of these clients. And that's why it's an indirect intrusive heap, because there's one level of indirection so that these structures, indirect structures can appear, each heap can contain a bunch of those, all of which refer back to the actual clients. All right? So, well, anyway, so we have those 3 different heaps to help us figure out which request to handle next. All right, I'm going to switch windows once again back to our terminal window. All right. There is some conditional compilation here. Originally, we thought there might be a 4th heap, the one that just keeps track of proportion or weight. But it turns out that is entirely subsumed by the ready heap, and so I believe used proc heap is always false, and therefore we don't incorporate the 4th heap into things currently. One other important detail that I missed. Coming back up here, this is the priority queue base, all right? And the reason why it's a base class is because it has 2 subclasses. One is for a pooled priority queue, where, such as an OSD might say, I'm ready for my next request, please give it to me. And that's a pull-based system. You could also imagine a push-based system as well. And so those are the 2 subclasses of priority queue base, a pull queue and a push queue. Now, it turns out that I believe that the 2 uses of Dmclock within Ceph, one is for the OSDs, the other is for RGW. I believe they both use just the pull-based queue, so we'll focus on that. But there is a whole push-based system as well. Much of the code is shared between the 2, which is why we have this base class to keep track of all the shared code of those two different subtypes. Okay. Kind of look through, trying to find the next interesting thing here. We have this enum class called next request type. And it could be, well, first of all, where I believe there's a Boolean somewhere in here that determines whether or not we enforce the limit. So the question comes in, if all of the clients are beyond their defined limit and the OSD is ready to do its next request, what should happen? Should there just not be a request there because all the clients have achieved their have already passed their limit until some more time goes by and then we can service more requests from them? Or the OSD is ready, why not give it something? All right? And so somewhere I believe there is a variable. Let me see if I can find it here quickly. I believe it's just a Boolean as to whether or not, where is it here? Whether we enforce the limit or not. Okay? And we either can or we can't, we can either allow it to be enforced or not have it enforced. Not popping out to me right now, but realize we have the two different ways of using it, either enforcing the limits or, when push comes to shove and the OSD is ready for another request, give it something even if everything is at their limit already. But when the limit is being enforced, this next request type comes into play. So when the OSD says, I would like your next request that's based on the priorities, it can either return a request. It could say there's no request in the system. We simply have none. Sorry. Or it can say all the clients have achieved their limit, but the next one again, the limit is something like 5 requests per second or something along those lines. So if we've already given this client 5 requests in the last second, it's already achieved its limit and it's supposed to be capped. We could say that, in 2 seconds, the next request will be ready. And that's what future is for. All right, so it allows the clients to be a little, the server side to be a little more sophisticated in how it handles things. And so we have those 3 possibilities. The next enum class is Heap ID. Again, this is that specifies whether we service a request during the reservation phase or the wait or proportional phase. And we're using the ready. So now we actually have 3 different terms for it. But we're using the ready queue here for that. So for the other phase, which is the wait, proportional, or it's based on the ready queue here. All right. Oh shoot! What did I just do? So there is this data structure that when a request is requested by the server, let's say the OSD to operate on, it says which type of request it is, returning, future, or none. And then we have a union here that either contains the heap ID, which is either reservation or ready, meaning that we are returning a request. And here's which phase it was returned, it's coming from. Or if it's future, returns a time instead, saying here is when the next request can be serviced. All right, so it's one or the other of those, which is why we have a union there. All right. The next big thing here is this client compare function. Again, it's templatized, and it's basically the function that's used to sort each of our 3 heaps. And the way it's sorted is based on the template parameters that come in when this structure is instantiated. So request tag field determines which of the fields. Is it the reservation, the wait, the limit, which is being used here? Whether we care about the value of ready. Again, things that are marked as ready means they're still within the limit. We haven't hit the limit yet, the cap. And the bool is whether or not we use the delta property in these calculations here. And so based on those, it looks complicated, but it's saying that given these two client records, which one should come first? Does client 1 come before client 2 or not? Okay? If client 1 should come before client 2, then it returns true. If either client 2 should come before client 1 or they're the same, then it returns false. And that is what's being used by the heap data structure in order to move the next item to the top of the heap by doing a sequence of comparisons and moving a client record up to the top of the heap. All right? And even though it looks complicated, because these are template parameters and whatnot, it probably compiles down to some relatively simple code based on what those template parameters are. Okay? And so now we can see that we have each of those 3 heaps. Again, we're not using the prop heap. That is compiled out. And that we supplied the comparison function for each of them. So, for example, the reservation heap here, it uses the reservation tag as its main thing for ordering things. It ignores the ready option, and it does not incorporate delta. All right. Whereas the ready heap, okay, where things are handled by wait, and things that have not achieved their cap, use the proportion field. I remember. Oh, the ready option raises. If something is ready, then it raises it. It makes that client more important in the heap, and we are going to incorporate delta in the ordering. All right. So it consolidates all that code nicely there. Okay. Again, there's a lot of bookkeeping in here, which I'm not going to go through. Okay. So here's the code for adding a request. It kind of gets complicated. It's called do add request. I believe there's a number of add request interface functions, all of which can get consolidated down to the do add request, which actually does the work of adding a request to the queue. And there's different kinds of cleanup which also have to be done. And so this, I believe, can trigger various kinds of cleanup as well. Okay. Do next request is the key function which determines which request is returned back to, say, the OSD when it's ready for its next request, and it has to go through the internal logic of Dmclock. Okay? So it first looks to see if the reservation heap is empty. If the reservation heap is empty, then all the heaps are empty. It means that there's no active clients currently, and it does return none in that specific case. And then it looks to see whether there is a request, pulls up the top request and sees whether its reservation is less than or equal to now. If it is, the work is done. It knows which request it needs to be handled, and the work is done. Now, if there is nothing which, if we've met all of our minimum reservations, then it has to go on to the next phase here, where it has to, let's see here. It first adjusts the limits heap, all right? And then, amongst those things that are ready, it looks to see what the top element is, make sure that it is ready, that the ready flag is true, and that the proportion is less than the maximum tag. So I'm drawing a blank as to why that bit of logic is there. And if it finds something which achieves that, then it returns that as the next request during the proportional phase, the ready phase. Now, once we get here, that means that we had nothing that we could schedule via reservation, nothing we can schedule via weight or proportion. And so now the question is whether what we do when we've achieved our limit. Do we ignore the limit and still return the next item nonetheless, or do we enforce the limit? And that's what this code here is doing, okay? And if we're allowed to break the limit and say we return something, we first do it by, I guess we do it by weight, okay? We first try and do it by weight, and if we can't do it by weight, we do it by reservation, okay? So we have a way of breaking the limit if we don't want to enforce the limit. And then there is some a bookkeeping which is done down below here. I guess this is the case now. Once we get to this point, nothing is scheduled, so make sure when we rerun the next reservation item or next limited item comes up, okay? So if we didn't find anything that we could return, we end up having to either return a future that says that wait until this time and something will be ready, or if there's nothing that's going to be ready soon, we return none, okay? And so that's all the logic there. There is some cleanup that needs to be done when clients might disappear. We have to clean up all the data structures that are associated with that particular client. And that's, I think, based on how long it's been since the client has sent a request. And if it's been a certain amount of time, we clean up the data structures associated with that particular client. And again, above, let me move my cursor down here, but basically, above this point is the common code. And then we have the specific code for the pull priority queue, and then down below that for the push priority queue. Okay? I am seeing that it's now almost 15 minutes in. Maybe I'll take a quick peek at the indirect intrusive heap, since that handles a lot of the key work for that. Well, there's two ways to go here. Let me quickly instead first show where Dmclock is to be found within the OSDs here. As we go from source OSD/scheduler, and there are different schedulers that we can use. One of which is the Mclock scheduler, which is comprised of these two files here. And if I run git blame on Mclock scheduler, you'll see that Sam just has basically rewritten all this code, and it did need to be rewritten back in September of 2019. So this code is actually new to me. I saw it for the first time today. But let me quickly show you that in this particular implementation, there are essentially three clients. One client is the actual client requests that are coming in from a variety of clients. All the clients that are sending requests to the cluster, their requests are mixed up as a single client from the viewpoint of Dmclock here. Okay? So we have one set of scheduling parameters for all clients. We have another one for background recovery. So Background cover is considered to be the second client in this particular system, and it has its requests. And then the third one is something called background best effort. I haven't looked through the code to see what gets scheduled under this particular client. That is our third client. So we're trying to achieve a certain fairness and a certain level of service between these three very broad, abstract sets of clients here that aren't real clients, but categories of requests, basically. Okay? So that's how the OSD handles Dmclock. If you want to know more about how RGW handles Dmclock, both Abhishek and Casey are the ones who've done all that code. I really can't speak to that. But perhaps for the last little bit, I'm going to quickly jump over here and go into the supports subdirectory. And we have some support classes and some tests for those support classes. And the key one here is this thing called the indirect intrusive heap, which, again, we instantiate 3 times on the server, once to order things based on reservation, once on wait, and once on limit, and once on whether they're ready, which combines both limit and wait. And so I'll take a very quick look at that. It's been a long time since I looked at this code, but the reason why it's intrusive, and maybe I have to go back to the picture. Let me switch windows once again. Is that each heap has a indirect reference to each of the clients. All right. And then when we manipulate a client and we say, okay, we're going to now service the request for client 1, that's going to need us to reevaluate and re-bubble up to the top of each of our 3 heaps which request will come next. It will affect everything. And so that means client 1 now might appear somewhere. It might not be at the top of any of those given heaps, and so we have to recalculate those. And so the client records have to know where in each of the 3 heaps they exist. So each of these client records on the server side has to have a number which says, in the reservation heap, we're at position 3, where it's an index. And in the ready heap, we're at position 5, and in the limit heap, we're at position 2. So when we then service this request, we can go in and adjust that client for each of the 3 heaps. Okay, and that's why it's an indirect intrusive heap. We have to have some intrusive data that we manage in each of the client records. All right. So I don't think we have enough time, and I don't know if my memory is clear enough since it's been so long to kind of go through all this. But that's basically what's happening here. And you'll see there are various operations to manage the heap. Here's our public interface. So whether it's empty or not, how many elements are in the heap, pushing items, removing items, binding items, and so forth. It handled all the kinds of functionality you would imagine. But I see we're at 5 minutes left for the hour, so maybe at this point, I'll just see if there are any questions out there. I realize it's a lot to absorb, so I can certainly appreciate that.
Eric, maybe you could speak a little bit about the performance potential areas you could see for performance improvement, or areas of the algorithm that are more expensive.
Yeah. If you go back to the server code, well, so some operations, when you choose a set of data structures to use, you try and optimize them for the operations that are occurring most often. Nonetheless, some other operations that need to be done you might have to sacrifice them somewhat. And I remember, let's see here. One is when you have to Here, there's even a comment here. When you need to remove requests by filter, I believe that the queues that the OSD have say you remove all. There are some functionality there which say remove all the requests that that this filter returns true for, which means that we have to then implement this in the library as well. And so I believe that's a relatively expensive operation, and there's even a little comment here that says because this is a deck, this can be relatively expensive as we have to go through and probably touch a bunch of other stuff in there. This code has been looked at and sifted through by a number of people, and actually the open source contributors in Asia associated with various telecoms have really done a lot of work in optimizing things, which is, for example, why the tag calculation is delayed, because they found that the algorithm works better when we use the most recent row and deltas to calculate those tags. So I'd say at this point, nothing pops out at me. Again, I probably haven't looked at this code in at least a year and a half to 2 years very closely. But Dmclock received a lot of attention there for a period of time. A lot of discussions going on as far as whether we were implementing it correctly based on the paper, whether the paper might have been vague in some points, or the paper might have been incorrect in some points, or missed a detail. And so I think we're close to there, but I'm sure other people who went through this with a fine-tooth comb probably find things that could nonetheless be improved. But I don't know of anything at this particular time. I guess to say those who are interested in working on this, again, there's, at least within the Ceph community, there are 4 people that I know that have been working on it. Sam has done a lot of work recently on it. Casey and Abhishek have done a lot of work on the RGW side, and of course I did some of the original work as well. And I'll only speak for myself, but I would certainly, if you have any specific questions, it might take me a while to answer them because it's been a while, but I am happy to answer questions on it. And I suspect the other 3 wouldn't mind either.
Feels like that's it. Thanks, Eric. That was great.
Thank you very much. Hopefully it made sense.
Yeah, it made sense to me at least.
Thanks.
Made a lot of sense. Thanks, Eric.
You're very welcome.